Hello there, and welcome to Sleepy Science Vault. Somewhere, right now, in the quiet dark between galaxies, there is a place where the laws of physics as we know them begin to break down. We call it a black hole. For most of human history, the night sky was simply a canvas of light, scattered stars, distant and unreachable, telling stories older than any civilization. But hidden within that darkness are objects so strange, so extreme, that they challenge the very foundations of what we understand about reality itself. Black holes are not empty voids. They are not holes in the traditional sense at all. They are regions where gravity has become so overwhelming, so absolute, that nothing, not even light, can find its way back out. Tonight, we're going to explore one of the most captivating ideas in modern theoretical physics. A question that sits at the edge of science and imagination alike. Could black holes be more than cosmic graveyards? Could they, in some way we don't yet fully understand, be cosmic wombs, giving birth to entirely new universes? It's a question that sounds like science fiction. And in many ways, it still lives in that hazy borderland between speculation and hard science. But the physicists who study this idea are not fantasists. They are serious researchers, wrestling with real mathematical problems that emerge when you push general relativity to its absolute limits. So let's begin gently, at the beginning. Some physicists have proposed that black holes could trigger the birth of new universes. This is not a fringe daydream whispered at the edges of academia. It's a genuine hypothesis, explored through serious mathematical frameworks, discussed in physics journals, debated at conferences. The core idea is almost poetic in its scope, that the very same collapse which seems to destroy matter in space and time, might, on the other side of that collapse, create something entirely new. A budding cosmos. A universe unto itself. It's worth pausing here to really sit with that idea. A black hole, an object defined by destruction and disappearance, might actually be a doorway. Not an ending, but a beginning. And yet, as beautiful as this idea is, we have to be honest about where the science actually stands. The idea is considered highly speculative, and scientists do not currently have direct evidence that black holes create new universes. This is important to understand from the very start. There is no telescope pointed at a black hole today that has confirmed a new universe blooming inside it. There is no experiment that has captured proof. What we have instead are mathematical models, equations that suggest this could be possible under certain theoretical conditions. The gap between mathematically possible and physically confirmed is enormous, and any honest exploration of this topic has to respect that gap. So why do scientists even entertain the idea at all? To understand that, we have to look at what we do know for certain about black holes, starting with their most famous feature. NASA's current black hole science pages still describe the event horizon as the boundary beyond which nothing, including light, can escape. This is the defining edge of a black hole. Not a physical surface you could touch or stand on, but a mathematical threshold, a point of no return. Once anything crosses this boundary, whether it's a wandering asteroid, a beam of starlight, or theoretically even information itself, it cannot come back. The event horizon isn't the black hole's surface. It's more like a permanent exit sign, one direction only, no return trip possible. And this single feature is what makes black holes so mysterious. We cannot see inside. We cannot send a probe in and have it report back. The event horizon isn't just a boundary in space, it's a boundary in what we are even capable of knowing. NASA still describes the event horizon as the one-way boundary beyond which nothing can escape, which is why any universe birth scenario must happen behind that boundary. And this is a crucial point to understand. If a new universe truly is forming inside a black hole, we would have no way of directly witnessing it. It wouldn't flash across our telescopes. It wouldn't send us a signal. Whatever happens beyond the event horizon, stays beyond the event horizon, as far as we, on the outside, are concerned. This single fact shapes everything about how scientists approach this question. The fact that black hole interiors remain inaccessible directly is one of the main reasons universe birth ideas remain speculative rather than confirmed. Think about what it means to study something you fundamentally cannot observe. Physicists studying black hole interiors are a bit like cartographers trying to map a country they can never actually visit, relying instead on shadows, gravitational effects, mathematical extrapolation, and careful reasoning about what the laws of physics demand, even in places we cannot see. It's a strange kind of science, confident in its mathematics, humble in its claims. Because the interior cannot be observed directly, black hole universe ideas remain logically possible but still unverified. This distinction, between logically possible and scientifically verified, is one worth holding on to gently as we move through tonight's journey. Many ideas in theoretical physics live in this space. They are not disproven. They are not confirmed. They exist as open questions, waiting patiently for either new mathematics, new observations, or entirely new physics to settle the matter one way or another. And that brings us to perhaps the deepest reason this whole idea exists in the first place. A major reason black hole origin ideas keep coming up is that classical general relativity predicts a singularity, which many physicists suspect must be replaced by new physics. A singularity, in the simplest terms, is a point where the mathematics of general relativity essentially breaks down, where density becomes infinite, where space and time curve so extremely that our equations simply stop making sense. Most physicists don't believe singularities are literally, physically real in the way the raw mathematics suggests. Instead, they suspect that singularities are a signal, a sign that our current theories are incomplete, and that some deeper, more complete theory of physics, perhaps merging gravity with quantum mechanics, is needed to describe what truly happens at the heart of a black hole. This is where the idea of universe birth begins to take a more specific shape. One version of the idea says a black hole's collapse may bounce instead of ending in a final singularity. Rather than matter collapsing infinitely inward, forever, into a point of zero size and infinite density, some models propose that quantum effects that only become significant at unimaginably small scales, could halt the collapse. Instead of crushing infinitely down, the collapsing matter might reach an extremely dense, but finite, state, and then bounce. not unlike a ball compressed to its absolute limit before springing back outward. In that picture, the bounce could form a new region of spacetime beyond our universe's visible horizon. This is where the idea becomes genuinely awe-inspiring. If the collapsing material bounces rather than vanishing into a singularity, that rebound could, according to these models, expand outward into a new region of spacetime entirely, a region causally disconnected from our own universe. Not a new universe floating somewhere out in our sky, visible if only we looked hard enough, but a truly separate expanse of space and time, budding off from the collapse itself, existing beyond anything we could ever observe from where we stand. It's the kind of idea that makes you look up at the night sky a little differently. Some black hole interior models are designed to resolve singularities by replacing them with a finite quantum region. Rather than allowing the mathematics to spiral into infinity, these models introduce quantum gravitational effects that essentially cap the collapse. Space doesn't crush down to an infinitely small point. Instead, it reaches some minimum, finite size, governed by the deep quantum structure of spacetime itself, and from there, the story continues. Whether that continuation means a bounce, a new universe, or something else entirely, remains one of the great open questions of theoretical physics. And so, as we drift through these ideas together tonight, we begin to see the shape of the mystery. Black holes, those silent, invisible giants scattered throughout the cosmos, may be far stranger than simple destroyers of matter and light. They may be sites of transformation, places where old physics ends, and, perhaps, in ways we don't yet understand, something new quietly begins. We'll continue exploring this idea further, moving deeper into the physics, the models, and the strange, beautiful possibilities that lie behind the event horizon, in the facts that follow. We left off drifting at the edge of the event horizon, imagining a collapse that doesn't end, but transforms. Let's continue gently from there. In those models, the center of a black hole may behave more like a transition zone than a true physical endpoint. This is a subtle but important shift in thinking. For a long time, the very center of a black hole, the singularity itself, was treated as a kind of cosmic full stop. The place where everything simply ends. Matter compressed into nothingness, time itself grinding to a halt. But in these newer models, that center isn't a wall. It isn't a final destination at all. It behaves more like a threshold, a place where one set of physical conditions gives way to another. Not an ending, but a passage. It's a quiet reframing, but it changes everything about how we imagine what's happening in there. Some versions of the idea treat the new universe as causally disconnected from the parent universe after formation. This means that once this new region of spacetime comes into being, it doesn't remain tethered to our universe in any meaningful way. No signal could pass between the two. No light, no gravity, no information of any kind. It would simply exist, on its own terms, following its own timeline, its own physical unfolding, completely sealed off from the universe that gave rise to it. In a strange way, it would be like a child growing up in a home so distant, so separated, that no letter, no phone call, no memory could ever cross the distance again. A universe, born and then entirely alone. Some black hole universe models try to explain the Big Bang as a transition rather than an absolute beginning. This is where the idea takes an unexpected turn and begins to reflect back on our own origins. For decades, the Big Bang has been described, in popular language at least, as the beginning. The start of time. The start of space. Before it, nothing, or perhaps a question that doesn't even make sense to ask. But some of these models propose something different. They suggest that what we call the Big Bang might not have been a true beginning at all. It might have been a transition. A moment where spacetime shifted from one state into another, perhaps even the very moment when our universe emerged from the collapse of something else entirely. The idea has been used to explain why the Big Bang might not have been a true beginning, but a transition from another spacetime. Imagine, for a moment, that our own universe, every star, every galaxy, every quiet night sky we've ever looked up at, began not from nothing, but from the collapse of a black hole in some other, older universe. That the immense density and heat we associate with the Big Bang wasn't a spontaneous appearance from nowhere, but rather the outward bounce of matter that had been crushed down on the other side of someone else's event horizon. It's a humbling thought. That our entire cosmic history might be, in some sense, an echo of someone else's ending. This theory is tied to the broader and still unconfirmed idea that our own universe might have formed inside a black hole. And this is where we begin to understand the true scale of what's being proposed here. This isn't simply a story about other, hypothetical universes forming inside distant black holes somewhere out in the cosmos. Some physicists have extended this reasoning inward, asking whether we ourselves, our galaxy, our sun, our quiet corner of existence, might be living inside the aftermath of a black hole's collapse. Not observing this phenomenon from outside, but existing as a direct result of it. It remains, of course, entirely unconfirmed. But its implications are enormous to sit with. Black hole universe ideas also appear in broader black hole cosmology models, which explore whether our own universe may have originated in a black hole. This entire area of study has grown into its own branch of theoretical exploration, often referred to as black hole cosmology. It isn't a single, unified theory, but rather a family of related ideas, each one asking variations of the same central question. What if the relationship between black holes and universes isn't one-directional? What if it's not simply our universe creates black holes, but potentially black holes create universes, in a kind of endless, generational chain? A 2025 article reported that some researchers think our universe may be trapped inside a black hole with no way out. This particular framing adds another layer to the idea, not just that we may have formed from a black hole's collapse, but that we may, in some very real sense, still be living inside one. Trapped, not in a sense of danger or immediate consequence to our daily lives, but trapped in the way an event horizon traps light, permanently, silently, without any possibility of escape to whatever lies beyond. It's a strange thought to hold while looking up at a clear night sky, stars scattered peacefully overhead, and wondering whether that sky itself might be the interior of something far larger and far stranger. The black hole universe hypothesis is being discussed as a competitor or alternative to standard cosmological origin stories. It's important to understand that this idea doesn't exist in isolation. Mainstream cosmology already has a well-supported framework, the standard Big Bang model, refined over decades through careful observation and evidence. Black hole cosmology doesn't erase that framework. Instead, it offers an alternative lens, a different way of interpreting the very earliest moments of our universe's history, one that some physicists find compelling enough to explore seriously, even while it remains outside the scientific mainstream. There are multiple competing versions of the idea, and they do not all use the same physics or reach the same conclusions. This is worth pausing on gently. When people hear black holes might create universes, it's easy to imagine one single, tidy theory. But the reality is far messier, and far more interesting. Different researchers, working from different mathematical frameworks, some rooted in quantum gravity, some in loop quantum cosmology, some in string theory, have proposed their own distinct versions of this idea. They don't always agree with each other. Some emphasize the bounce. Some emphasize the finite quantum core. Some focus on cosmological implications, others on the black hole's interior structure alone. It's less like a single map, and more like a collection of different explorers, each sketching their own version of an unseen landscape. And among these explorers, one name in particular stands out for the sheer creativity of his proposal. Lee Smolin's proposal is often called cosmological natural selection. It's a strikingly original idea, one that borrows, quite deliberately, from the language of biology. Smolin suggested that universes might reproduce through black holes in a manner that echoes evolution itself. Each black hole birthing a new universe, with slightly varied physical constants, slightly different rules governing gravity, particle masses, and fundamental forces. Universes that happen to produce more black holes would, in this framework, produce more offspring universes, passing along, in a strange cosmic inheritance, the physical laws best suited to creating still more black holes. It's less like a single explosive beginning, and more like a vast, slow, cosmic family tree. We'll spend more time with this particular idea very soon, exploring exactly how Smolin imagined this process working, and what it might mean for the deep structure of reality itself. For now, let's simply let this thought settle quietly. Universes, perhaps, not appearing once and existing forever unchanged, but evolving, generation after generation, through the silent, hidden mechanism of black holes scattered across an unimaginably vast, and possibly self-replicating, cosmos. Let's return now to that idea we left drifting in the quiet, the thought of universes not simply appearing, but evolving. Lee Smolin's cosmological natural selection hypothesis says each black hole may produce a daughter universe. It's a term worth sitting with for a moment. Daughter universe. Not a copy. Not an identical twin. A descendant. Something born from a parent, carrying traces of where it came from, and yet capable of being subtly, quietly different. In Smolin's vision, every black hole scattered across every galaxy, every one of those silent, invisible giants, might be a kind of birth event. Not the end of matter's story, but the beginning of an entirely new one, unfolding somewhere we can never see. In Smolin's model, the physical constants of the daughter universe may differ slightly from the parent universe. This is where the idea becomes especially delicate and strange. We tend to think of the laws of physics as fixed, absolute. The strength of gravity, the mass of a proton, the speed of light, these feel like bedrock certainties, true everywhere and always. But in this model, those constants aren't necessarily locked in place across all of existence. Each time a new universe is born through this process, its fundamental constants might shift, ever so slightly, from the universe that created it. Small variations. Subtle differences. Enough to matter over immense stretches of cosmic time. The theory suggests physical constants could slowly vary from one universe to the next, rather than staying identical. Imagine, if you will, an almost imperceptible drift, generation after generation of universes, each one slightly different from the last, the way a whispered message changes subtly as it passes from person to person down a long, quiet line. Over countless generations, these small variations could accumulate into something significant. Universes with slightly stronger gravity. Slightly different chemistry. Universes where stars form more easily, or less easily. Universes that may be, in some fundamental sense, more or less suited to producing more black holes. And this is where Smolin's idea takes its most creative turn. The idea borrows the logic of biological evolution, where universes that make more black holes would leave more descendants. On Earth, evolution works through a beautifully simple principle. Organisms that are better suited to their environment tend to survive longer and reproduce more successfully, passing their traits on to the next generation. Smolin imagined something remarkably similar playing out on a cosmic scale. Universes, in this framework, reproduce through black holes. And so, universes that happen to be especially good at forming black holes, whatever set of physical constants makes that possible, would naturally produce more daughter universes, carrying those same successful traits forward. In that framework, universes that produce more black holes would be selected because they leave more descendants. It's not selection in the sense of a conscious choice being made anywhere. There's no cosmic decision-maker, weighing options and choosing which universes deserve to continue. It's simply a numbers game, playing out across almost incomprehensible timescales. Universes especially good at generating black holes simply end up, mathematically, with more descendants than universes that aren't. And so, over countless generations, the population of universes would gradually shift, becoming dominated by those particularly well-suited to producing black holes. It's evolution, stripped of biology entirely, and applied instead to the very fabric of existence. The hypothesis is partly motivated by the question of why the laws of physics seem finely tuned for stars, chemistry, and life. This question, the question of fine-tuning, has quietly troubled physicists for decades. Our universe seems to sit in a remarkably narrow, precise range of conditions that allow for stars to form, for complex chemistry to unfold, and eventually, for life itself to emerge. Adjust gravity even slightly. shift the mass of certain particles by the smallest fraction. And stars might never ignite. Atoms might never bond the way they do. The universe, as we know it, simply wouldn't exist in a form capable of producing us. Smolin's proposal offers one possible, speculative answer to that deep and lingering mystery. If universes that produce black holes tend to leave more descendants, and if the very same conditions that make black holes possible also happen to favor stars, and heavy elements, and complex chemistry, then perhaps it's not a coincidence at all that our universe seems so remarkably suited for both black holes, and for us. Perhaps it's simply what remains, after countless generations of cosmic natural selection. Some versions of the hypothesis try to make testable predictions, such as whether our universe is unusually good at producing black holes. And this is an important point to hold on to gently, especially amid an idea this speculative. Genuine scientific hypotheses, even highly unconventional ones, ideally need to offer some way of being tested, some prediction that could, in principle, be checked against observation. Smolin's hypothesis attempts exactly that. If cosmological natural selection is correct, our universe should be unusually efficient at producing black holes, compared to universes with even slightly different physical constants. It's an ambitious, difficult thing to verify, but its very attempt at testability is part of what has kept this idea alive in serious scientific conversation, rather than dismissed as mere speculation. Let's shift now, gently, to another physicist, who approached this same mystery from an entirely different mathematical direction. Nikodym Poplawski's approach uses Einstein-Cartan gravity, where spacetime torsion can prevent an infinite density singularity. Where Smolin focused on evolution and selection across generations of universes, Poplawski's work dives deeper into the underlying physics of the collapse itself. Einstein-Cartan gravity is a variation of general relativity, one that introduces an additional property of spacetime called torsion. Without getting lost in complex mathematics, torsion can be understood, gently, as a kind of built-in twisting within the geometry of space and time itself. And in Poplawski's models, this torsion becomes profoundly important, because it can act as a natural brake, preventing collapsing matter from crushing down into an infinitely dense singularity. In Poplawski's model, gravitational collapse inside a black hole can lead to a bounce that forms a new expanding universe. Rather than collapsing forever, inward, without end, the torsion within Einstein-Cartan gravity provides a kind of resistance, a force that grows immensely powerful at extremely high densities, eventually halting the collapse entirely. And once that collapse halts, the same immense energy that drove the collapse inward reverses. It bounces outward instead. Not back into our own universe, but into a new, expanding region of spacetime. A new universe unto itself, born from the sheer, immense pressure of collapse, finding release, not through destruction, but through a kind of rebirth. That idea is linked to a big bounce version of cosmology, where collapse is followed by re-expansion instead of a true end. This concept, often referred to as a big bounce, offers a compelling alternative to the traditional picture of a singular Big Bang, appearing from nothing, with no prior cause. Instead, in bounce cosmology, collapse and expansion become two chapters of a single, continuous story. An ending, followed inevitably by a beginning. A crushing down, followed by an explosive, outward release. It's a quiet, elegant symmetry threading through these different models, isn't it? Whether we're speaking of Smolin's evolving generations of universes, or Poplawski's torsion-driven bounce, the deep, underlying theme remains strikingly similar. Collapse isn't necessarily the final word. Somewhere, in the mathematics of these speculative models, endings quietly transform into beginnings. We'll continue exploring this rich, strange landscape further, drifting even deeper into the physics behind these models, in the facts that follow. Let's continue drifting through these ideas, following the thread a little further. A newer variant suggests gravitational collapse can rebound because quantum effects prevent an infinite singularity. This particular framing shifts our focus once more, away from torsion and geometry, and towards something even deeper, the strange, probabilistic world of quantum mechanics itself. In this version of the idea, it isn't a twisting of spacetime that halts the collapse. It's the fundamental, quantum nature of matter and energy at extremely small scales. As collapsing material approaches unimaginable density, quantum effects begin to dominate, effects that simply don't exist in our everyday, classical experience of the world. And these effects, in certain models, become powerful enough to prevent that final, infinite crush, allowing the collapse to reverse instead, and rebound outward. The mechanism would likely require a theory of quantum gravity, which we do not yet have. And here, we arrive at one of the deepest, most humbling truths in modern physics. Quantum mechanics governs the very small, particles, atoms, the strange probabilistic dance of subatomic reality. General relativity governs the very large, stars, galaxies, the sweeping curvature of spacetime itself. Both theories are extraordinarily successful, verified again and again through careful experiment and observation. And yet, they don't fit neatly together. At the heart of a black hole, where immense mass is compressed into an impossibly small space, both theories are needed simultaneously, and currently, we simply don't have a complete theory of quantum gravity capable of describing what truly happens there. It's a quiet reminder that these black hole universe ideas exist, in many ways, at the very edge of human understanding itself. Loop quantum gravity is one of the main frameworks used to explore what happens when singularities are removed from black hole interiors. Among the various attempts to bridge this gap between quantum mechanics and gravity, loop quantum gravity stands out as one of the most actively developed. Rather than treating spacetime as smooth and continuous, the way general relativity traditionally does, loop quantum gravity proposes something quite different, that space itself, at the very smallest scales, may be built from tiny, discrete units. Not a smooth, flowing fabric, but something more like a fine, granular structure, individual threads woven together into the appearance of smoothness, much the way a photograph, viewed closely enough, dissolves into individual pixels. Some theories tie universe creation to loop quantum gravity, which replaces singularities with quantum geometry effects. Within this framework, the singularity, that troublesome point of infinite density predicted by classical general relativity, simply doesn't appear the same way. Because spacetime itself has this granular, quantum structure, there's a natural limit to how tightly it can be compressed. Long before reaching true infinite density, the quantum geometry of spacetime intervenes, and in some models, this intervention becomes the very mechanism that allows a new, expanding universe to emerge from the collapse. Some modern black hole cosmology papers use loop quantum gravity to argue that singularities can be resolved mathematically rather than left infinite. This might sound like a small, technical detail, but its implications run remarkably deep. If singularities can be mathematically resolved, rather than simply left as unsolvable infinities, it suggests that our equations aren't broken. They're simply incomplete in their classical form, and require this deeper, quantum layer to fully describe what's truly happening. It offers physicists a way forward, not abandoning general relativity, but extending it, refining it, allowing it to gracefully hand off its description of reality to quantum gravity, right at the threshold where it would otherwise fail. In that framework, quantum geometry can create a repulsive effect strong enough to halt collapse at extreme density. It's a striking image, if you sit with it for a moment. As matter collapses inward, crushed by its own immense gravity, it approaches this fine, granular quantum structure of spacetime itself. And rather than passing through it effortlessly, into infinite density, the quantum geometry pushes back. A repulsive force, emerging not from any conventional matter or energy, but from the very structure of space at its most fundamental level. Strong enough, in these models, to halt the collapse entirely, and set the stage for a bounce. Black hole interiors are now often discussed as places where spacetime may not remain a smooth classical geometry. This represents a genuine shift in how physicists think about black holes altogether. For much of the 20th century, black holes were described purely through the smooth, elegant mathematics of classical general relativity. But increasingly, researchers recognize that deep within a black hole, in that extreme, compressed environment, spacetime likely stops behaving smoothly at all. It becomes something stranger. Something quantum. Something that our everyday intuition, built entirely from experiences in the smooth, classical world around us, simply isn't equipped to imagine clearly. Some recent black hole research focuses on how spacetime itself may emerge from more fundamental quantum information. And this idea pushes even further into genuinely profound territory. Rather than treating spacetime as a basic, fundamental stage upon which physics unfolds, some researchers now explore the possibility that spacetime itself isn't fundamental at all. That it might instead emerge, the way temperature emerges from the collective motion of countless individual particles, from some deeper layer of quantum information. In this view, the smooth fabric of space and time that we experience so intuitively, might simply be what a deeper, more fundamental quantum reality looks like, from our particular vantage point within it. Researchers continue to use black holes as probes for how spacetime itself might emerge from quantum degrees of freedom. Black holes, in this sense, have become something far more than simply extreme astrophysical objects worth studying for their own sake. They've become theoretical laboratories, natural, cosmic experiments where the ordinary rules seem to break down, offering physicists a rare and precious window into how a deeper, quantum foundation of reality might actually work. Because black holes push spacetime to its absolute limits, they've become one of the most valuable places, in all of theoretical physics, to search for clues about what lies beneath. In that view, black holes are useful laboratories because they sit at the boundary between gravity, quantum theory, and thermodynamics. This is perhaps the quiet, unifying thread running through everything we've explored so far. Black holes occupy a truly unique position in physics. They are governed by gravity, shaped by the sweeping curvature of spacetime. They involve quantum effects, particularly near the event horizon, where quantum mechanics simply cannot be ignored. And remarkably, they also obey the laws of thermodynamics. Black holes have temperature, they have entropy, they can, in certain theoretical frameworks, even evaporate slowly over time. Three enormous pillars of physics, gravity, quantum theory, and thermodynamics, all meeting, quietly, at the edge of a black hole's event horizon. It's little wonder, then, that so many physicists find themselves drawn to these strange, dark objects, not merely as astronomical curiosities, but as genuine keys, perhaps, to some of the deepest mysteries the universe still holds. We'll continue on from here, moving further into these ideas, in the facts that follow. Let's stay with this thread a while longer, following it into even stranger, more elegant territory. Black hole cosmology remains connected to the broader question of whether spacetime geometry can change phase, like matter changing state. It's a curious way to think about the fabric of the universe, isn't it? We're used to thinking of phase changes in the context of everyday matter. Water freezing into ice. Ice melting into water. A liquid boiling away into vapor. Each of these transitions involves the same underlying substance, simply rearranging itself into a different structure, under different conditions. Some physicists now wonder whether spacetime itself might behave in a strikingly similar way. Whether, under the extreme conditions found at the heart of a black hole, the very geometry of space and time might shift, transitioning from one phase into another, the way water transforms into ice under sufficient cold. Black hole cosmology is increasingly linked to the idea that spacetime itself may be an emergent phenomenon rather than a fundamental one. This is a thread we touched on gently before, but it's worth letting it settle a little deeper here. If spacetime isn't truly fundamental, if it emerges instead from something more basic, some underlying quantum structure we don't yet fully understand, then perhaps it shouldn't surprise us that spacetime could also transform, or transition, or even, in some circumstances, give rise to entirely new regions of itself. A fundamental thing tends to feel fixed, unchanging, eternal. An emergent thing, by contrast, often carries within it the possibility of change, of different configurations, different phases, different outcomes. If spacetime is emergent, then a new universe born from a black hole could be a natural outcome of deeper microscopic physics. This idea offers something quite comforting, in its own strange way, amid all this speculation. If spacetime truly does emerge from some deeper quantum reality, then a new universe forming from a black hole's collapse wouldn't need to be some wildly exotic, singular exception to the rules. It could simply be a natural, expected consequence of how that deeper, microscopic physics behaves under sufficiently extreme conditions. Not a miracle. not a strange departure from how reality functions. Simply, physics, playing out exactly as it should, at a scale, and under conditions, we're only beginning to understand. Some theoretical papers now treat black holes as places where quantum geometry and classical geometry must both be used to get a complete picture. This reflects a growing recognition, within contemporary theoretical physics, that neither classical general relativity nor quantum theory alone can fully capture what's happening within a black hole. Far from the center, out near the event horizon and beyond, classical geometry still describes things remarkably well, the same equations that predict the orbits of planets, the bending of starlight, the behavior of GPS satellites overhead. But as you move deeper, closer to the core, that classical picture gradually breaks down, and quantum effects become impossible to ignore. A complete picture, these researchers argue, requires holding both frameworks together, classical and quantum, each contributing its part to the whole. The quantum correction approach is attractive because it preserves standard black hole behavior far from the center while changing only the extreme interior. There's a certain elegance to this approach, worth appreciating gently. It doesn't require throwing away everything we already know about black holes, all the decades of careful, well-tested physics describing their outer regions, their gravitational pull, their effect on light and matter nearby. Instead, it makes a much more modest, targeted claim. Out here, near the edges, everything behaves exactly as classical physics predicts. It's only deep within, at the most extreme densities imaginable, that quantum corrections become necessary, gently reshaping our understanding, right at the very core, without disturbing everything we've already confirmed further out. In several of these models, the event horizon is kept close to the classical black hole picture even while the deep interior is quantum corrected. This means that, from the outside, looking in, a black hole modified by these quantum corrections would appear remarkably similar to the black holes described by traditional general relativity. Same event horizon. Same characteristic bending of light. Same fundamental behavior, as far as any outside observer could measure. The differences, the truly strange and transformative physics, remain hidden, tucked away deep within the interior, quietly reshaping what happens at the very heart of the collapse, without announcing themselves to the universe outside. Theoretical work now studies whether black holes can be analytically extended into white hole regions across the horizon. Here, we encounter a genuinely fascinating counterpart to the black hole, an idea that seems to mirror it directly. If a black hole is defined by matter falling in, and never escaping, then a white hole represents almost the opposite. A region from which matter can only flow outward, and can never fall back in. Some theoretical models suggest that the mathematics describing black holes can actually be extended, quite naturally, into these white hole regions, hinting at a hidden continuity between the two, joined together across the boundary of the event horizon itself. In those models, the black hole interior can be extended through a white hole region instead of ending at a hard singularity. Rather than the collapse simply terminating in that troublesome singularity we've discussed before, some models propose a smoother, more continuous story. Matter collapses inward, reaches an extreme, quantum-corrected core, and then, rather than ending there, the mathematics extends outward again, into a white hole geometry. The story doesn't stop. It transforms. What began as a collapse quietly becomes an expansion, just on the other side of a boundary we, from our vantage point, can never directly witness. A popular version of the idea says black holes may be connected to wormholes, not just isolated regions of spacetime. This is where the imagery becomes especially vivid and easy to hold on to. Rather than picturing a black hole as an isolated void, swallowing matter and simply ending its story there, some models describe something closer to a tunnel. A passage, connecting one region of spacetime to another, through this strange combination of black hole and white hole geometry, often referred to as a wormhole. Not necessarily a tunnel one could travel through, in any practical sense, but a genuine mathematical bridge nonetheless, threading between different regions, perhaps even different universes altogether. In that picture, a black hole could be the entrance and a white hole the exit of a larger cosmic tunnel. It's a beautifully simple way to hold this idea in mind, as we drift toward the end of this segment. Matter falls into the black hole, here, in our universe, crosses that quiet, mysterious event horizon we've spoken of so often tonight, and rather than meeting a final, destructive end, continues onward, through this hidden bridge, emerging instead through a white hole, somewhere else entirely. Perhaps in some far distant region of our own universe. Perhaps, in the more speculative versions of this idea, somewhere else altogether, in a universe of its own. There's still so much more to gently explore within this idea, the mathematics behind these wormhole connections, and what they might mean for the deep structure of reality itself. We'll continue drifting through it all, in the facts that follow. We pick up now from that image of a tunnel, black hole as entrance, white hole as exit, some vast bridge threading between one region of spacetime and another. Let's continue to follow this thread outward. Some hypotheses describe our universe as a nested structure, like a cosmic Russian doll inside a parent universe's black hole. It's a striking image to sit with quietly. A Russian doll, of course, is a toy built from layers. Open the largest doll, and there's a smaller one waiting inside, and inside that one, smaller still, each nested perfectly within the last. Some cosmologists imagine reality unfolding in a similar way. Our universe, vast as it feels to us, its billions of galaxies, its unimaginable distances, its own black holes scattered quietly throughout, might itself be nested inside a black hole belonging to some larger, parent universe. And within our own universe, other black holes might, in turn, be quietly forming still smaller universes of their own. Layer after layer. Nested, endlessly, in either direction. It's the kind of thought that can make a person feel very small and very large, all at once. Researchers have studied whether the black hole and white hole masses should be of the same order in these bounce models. Now, let's move a little closer to the actual mathematics behind these ideas, gently, without losing the calm rhythm of the story. If a black hole truly does connect to a white hole, through some kind of bounce, a natural question arises. Should the mass of that white hole match the mass of the black hole that formed it? It sounds like a simple, almost bookkeeping kind of question, but it turns out to carry real physical weight. If the masses were wildly different, it would suggest energy either appearing from nowhere or vanishing without explanation, somewhere in the process. So researchers have carefully examined whether these two masses, black hole and white hole, should indeed be of the same order, roughly matching one another, to keep the physics consistent and well-behaved. A 2019 quantum gravity study found that a classical black hole singularity can be replaced by a homogeneous expanding universe in the interior. This finding offers something wonderfully concrete, amid so much speculation. Rather than remaining purely theoretical, researchers running detailed quantum gravity calculations found that the classical singularity, that troublesome point of infinite density predicted by Einstein's equations alone, doesn't have to appear at all. In its place, their calculations produced something remarkably different, a smooth, homogeneous, expanding universe, forming quietly within what would otherwise have been the black hole's interior. Homogeneous, meaning uniform, roughly the same in every direction, much like our own universe appears to be, on the largest scales, when we look out at the night sky. It's a genuinely lovely result, mathematically. Where classical physics predicted an ending, this particular quantum gravity approach found a beginning. That same study found little or no deviation from classical Schwarzschild geometry before the bounce in the sub-Planckian regime. This detail matters quite a bit, and it's worth taking gently, one piece at a time. The Schwarzschild geometry is simply the standard, well-established mathematical description of a non-rotating black hole, first worked out over a century ago, and confirmed through decades of careful observation. The sub-Planckian regime refers to conditions where the density, while extreme, hasn't yet reached the absolute smallest, most fundamental scale of length that physics recognizes, the Planck scale, an almost unimaginably tiny distance where quantum gravity effects become truly dominant. What this particular study found was reassuring, in its own quiet way. Right up until matter reached that extreme sub-Planckian density, everything behaved almost exactly as classical Schwarzschild geometry predicted. No strange surprises. No early deviations. The familiar physics held firm, all the way up until the very last, most extreme moment, right at the threshold where quantum gravity finally takes over. The model in that paper did not find evidence for white hole horizon formation in the cases it examined. Now here, we have to be honest and gentle about the limits of what any single study can actually show. It would be easy to imagine that once physicists find one promising mathematical bounce, everything neatly falls into place, black hole becomes white hole, tunnel forms, new universe unfolds, story complete. But real research rarely offers such tidy endings. In this particular paper, examining these specific cases, the researchers did not find evidence that a white hole horizon actually formed, the way some of the more elegant tunnel and bridge pictures we explored earlier might suggest. This doesn't disprove the broader idea. It simply reflects how careful, rigorous, honest this field of research tends to be, willing to report what the mathematics actually shows, rather than what might simply feel more satisfying or more complete. Science, even at its most imaginative, remains carefully honest about its uncertainties. The post-bounce geometry in these models can depend on the choice of quantum state used in the calculation. This is a subtle, but genuinely important point, and it helps explain why so many different, sometimes conflicting results appear across this entire field. In quantum mechanics, systems aren't always described by a single, definite configuration. Instead, they're often described by a quantum state, a kind of mathematical description capturing the full range of possibilities available to a system. And it turns out that the specific choice of quantum state used, right at the heart of these bounce calculations, can meaningfully shape what the resulting post-bounce universe actually looks like. Different quantum states can lead to different geometries, different behaviors, different outcomes entirely. It's a little like asking several different, equally skilled artists to paint the same misty landscape, each working from a slightly different vantage point. The underlying scene may be shared, but the resulting paintings can differ substantially, depending on where, exactly, each artist chose to stand. Some effective black hole models use polymer-like deformations of gravity, which are inspired by loop quantum gravity ideas. Let's drift a little further into the mathematical texture of these theories, gently, without losing our calm pace. We spoke earlier about loop quantum gravity, and its proposal that spacetime, at the smallest scales, might have a discrete, granular structure, rather than being smooth and continuous. Some researchers have built what are called effective models, simplified, more manageable mathematical frameworks, designed to capture the key physical effects of loop quantum gravity, without requiring the full, extraordinarily complex machinery of the complete theory. These effective models often use something called polymer-like deformations, a term borrowed, loosely, from the image of long, discrete, chain-like structures, echoing that same granular, thread-like picture of quantum spacetime we touched on before. Researchers studying deformed gravity have found that keeping the constraint algebra closed is highly restrictive. Now, this particular detail moves into genuinely technical territory, and it's worth taking slowly and gently. In general relativity and its various quantum extensions, there are deep mathematical consistency requirements, often described through something called a constraint algebra. Without drifting too far into the underlying mathematics, it's enough to understand this. The constraint algebra is essentially a mathematical structure ensuring that a theory remains internally consistent, that it doesn't contradict itself, that different ways of calculating the same physical situation always agree with one another. Researchers working with these deformed, polymer-like models of gravity have found that keeping this constraint algebra properly closed, properly consistent, is remarkably difficult. Highly restrictive, as the researchers describe it, meaning only a very narrow, carefully chosen set of modifications actually preserve the theory's internal consistency, while countless other, seemingly reasonable modifications quietly break it. It's a humbling reminder of just how delicately balanced these theoretical frameworks truly are. In the spherically symmetric sector, non-trivial deformations can still produce consistent effective black hole interiors. Despite those significant restrictions we just explored, there remains genuine, meaningful progress here. When researchers narrow their focus specifically to spherically symmetric situations, meaning, essentially, black holes shaped like a perfect sphere, without rotation or other complications, a reasonable simplification for a great deal of foundational theoretical work, they've found that certain non-trivial deformations, meaningful, genuine modifications to the classical theory, can still produce fully consistent effective descriptions of a black hole's interior. It's a delicate, hard-won mathematical achievement, proof that even within such tightly constrained territory, there remains real room for these quantum-corrected models to exist, coherently, without falling apart under their own contradictions. These models are often framed as a way to test whether deformed covariance can survive once you move beyond simplified symmetry assumptions. And this brings us to a lovely, quiet resting point for this particular stretch of our journey. Deformed covariance refers to a modified, quantum-corrected version of one of general relativity's most cherished and fundamental principles, the idea that the laws of physics should look the same and remain consistent, regardless of how we choose to describe space and time, regardless of our particular coordinate system or point of view. Researchers want to know whether this deformed version of covariance, born from these quantum modifications, can continue holding up, remaining consistent and well-behaved, even once the simplifying assumption of perfect spherical symmetry is gradually relaxed, moving closer, step by careful step, toward the messier, more complicated, more realistic black holes we might actually expect to find scattered throughout our universe. It's slow, painstaking work. Testing, refining, checking whether these elegant mathematical ideas can survive contact with genuine physical complexity, rather than only working neatly, within the safety of simplified, idealized cases. And perhaps that's part of what makes this entire field so quietly compelling. Not the promise of easy answers, or neatly resolved mysteries, but the patient, careful, honest pursuit of understanding, even when that understanding arrives slowly, incompletely, one small mathematical result at a time. We'll continue, gently, from exactly this point, carrying this same careful, curious spirit forward into the facts that follow. Let's continue drifting deeper, following this thread into some of the most careful, quiet mathematics in modern physics. Newer work on black hole interiors explores the quantum boundary near Planck curvature, where the sum over geometries may terminate. There's a particular concept worth sitting with gently here, the idea of a quantum boundary. As matter collapses ever inward, spacetime curves more and more sharply, approaching what physicists call Planck curvature, a scale so extreme, so far beyond anything we encounter in ordinary experience, that our usual mathematical tools begin to lose their footing. Some newer research explores what happens right at this threshold, using an approach borrowed from quantum theory called a sum over geometries, essentially, adding together every possible shape spacetime could take, weighted by probability, to arrive at a complete quantum description. And near this extreme boundary, some of these calculations suggest that sum simply terminates, comes to a natural, mathematical stopping point. Not an explosion into infinity, and not a smooth continuation either, but something more like a quiet, well-defined edge. These interior studies matter for universe creation ideas because they show how a black hole core might turn into a new spacetime region without needing a classical singularity. This is where all of this careful, technical work quietly circles back to the larger story we've been following tonight. If these boundary calculations are correct, they offer a genuine mathematical pathway, a way for a black hole's core to transform into something new, some entirely different region of spacetime, without ever needing to pass through that troublesome, infinitely dense singularity at all. The transition itself becomes the point. Not a destructive ending, but a genuine handoff from one region of geometry into another. And this quiet mathematical possibility opens a door to something else entirely, something that has puzzled physicists for decades. One proposal says the black hole interior could preserve information through the transition, helping address the black hole information paradox. Let's slow down here and take this idea gently, piece by piece, because it touches on one of the deepest, most enduring puzzles in all of theoretical physics. If a black hole's interior genuinely transitions into a new region of spacetime, rather than simply crushing everything down into oblivion, then perhaps whatever fell into that black hole, all the intricate, detailed information describing exactly what that matter was, how it was arranged, its full quantum description, might somehow be preserved through that transition, rather than being permanently lost. Information recovery is one reason black hole universe ideas remain scientifically interesting, because they overlap with the black hole information problem. This connection matters a great deal, and it helps explain why serious physicists continue taking these speculative universe birth ideas seriously, rather than dismissing them purely as imaginative curiosities. They don't exist in isolation. They intersect, quite directly, with one of the most pressing open questions in fundamental physics, a question that has occupied brilliant minds for well over 50 years now. The black hole information paradox remains important because resolving it could also clarify how gravity and quantum mechanics fit together. At its heart, the paradox asks a deceptively simple question. When something falls into a black hole, and that black hole eventually evaporates away, very slowly, over unimaginable stretches of time, through a process theorized by Stephen Hawking, what happens to all the information that fell in? Quantum mechanics insists that information can never truly be destroyed. Not completely, not permanently. It might become scrambled, rearranged, wildly difficult to reconstruct in practice, but the fundamental rules of quantum theory suggest it must, in principle, still exist somewhere. Yet the earliest calculations of black hole evaporation seem to suggest exactly the opposite, that Hawking radiation carries no such information at all, and once a black hole fully evaporates, whatever information fell in simply vanishes forever. This apparent contradiction between two of physics' most trusted, most thoroughly tested frameworks, quantum mechanics and general relativity, is precisely why the paradox has remained such a persistent, deeply important puzzle. The black hole information paradox is now often studied through the Page curve, which tracks whether information can come back out during evaporation. Named after physicist Don Page, this curve offers a way of tracking, mathematically, how much information should be entangled between a black hole and the radiation it emits, over the entire course of its evaporation. If information truly is preserved, the Page curve predicts a very specific pattern, rising for a while, then gradually turning, and falling back down, as the black hole's final evaporation approaches. For a long time, this specific curve, this precise turning behavior, proved remarkably difficult to reproduce through direct calculation, which only deepened the mystery further. Newer approaches use concepts like entanglement islands and quantum extremal surfaces to explain how evaporating black holes can still preserve information. In more recent years, physicists have developed genuinely new mathematical tools to tackle this exact problem, tools with names as evocative as the ideas they represent. Entanglement islands. Quantum extremal surfaces. Without drifting too deeply into their formal definitions, we can hold these ideas gently, in outline. They involve identifying specific regions, hidden within the black hole's interior geometry, that become quietly, unexpectedly linked, through quantum entanglement, to the radiation escaping outward. These hidden regions, these islands, appear to carry exactly the missing information needed to reproduce that elusive page curve correctly. Some recent work on black holes uses islands as a way to explain how information can still be recovered from Hawking radiation. It's a rather beautiful image, when you let it settle. Small, hidden islands of information, tucked away within the geometry of a black hole's interior, quietly connected, through the deep strangeness of quantum entanglement, to the faint radiation drifting outward into space. Rather than information simply vanishing into nothingness, these calculations suggest it remains threaded, subtly, invisibly, into the relationship between what's inside the black hole and what eventually escapes. The island idea is part of why many physicists think black hole evaporation may be compatible with information conservation after all. This represents a genuinely significant shift in how the physics community approaches this decades-old puzzle. Where once it seemed as though black hole evaporation might simply violate one of quantum mechanics' most sacred principles, this newer island framework offers a mathematically consistent way for information to survive the process after all. Not through some exotic new form of matter, or some entirely new force of nature, but through a deeper, more careful accounting of quantum entanglement, and the subtle geometric structures woven throughout a black hole's interior. The island framework is one of the clearest recent examples of a mechanism that lets information reappear in Hawking radiation calculations. And it's worth pausing here, gently, to appreciate just how significant this really is, within the broader story we've been following all evening. Progress on ancient, seemingly intractable puzzles in physics tends to arrive slowly, often through small, careful, technical advances rather than sudden, dramatic breakthroughs. The island framework represents exactly this kind of quiet, meaningful progress, a genuine mechanism, grounded in careful mathematics, offering a real path toward resolving one of the most stubborn contradictions between gravity and quantum theory. And in a strange, wonderful way, all of this circles back to where we began tonight. Black holes, once imagined purely as points of destruction and disappearance, keep revealing themselves, through decades of patient, careful research, as something far richer. Places where information may be preserved, rather than destroyed. Places where collapse may transition into new beginnings, rather than simple endings. Places where the deepest laws of physics, gravity, quantum mechanics, and thermodynamics, all quietly meet, and perhaps, in ways we're only beginning to understand, learn to speak the same language. We'll rest here for now, gently, and continue drifting through the remaining mysteries, in the facts that follow. We continue now, following this same quiet thread a little further, into an idea that reshapes, quite fundamentally, how physicists think about black holes altogether. Some modern reviews argue that the outside of a black hole may contain a full redundant copy of the information from the inside, in a quantum gravity sense. Let's sit with this one gently, because it asks us to release a very natural, intuitive assumption. We tend to imagine inside and outside as two entirely separate places, holding entirely separate information, the way a locked room holds its contents apart from the hallway outside it. But some of the most careful modern theoretical reviews suggest something far stranger. That, in a genuine quantum gravity sense, the information describing everything within a black hole might also exist, redundantly, encoded somewhere in the structure of the region outside it. Not a copy stored somewhere obvious, or easily accessible, but woven, subtly, into the deep quantum structure of the spacetime surrounding the black hole itself. That redundancy idea changes how physicists think about what inside and outside mean for black holes. And this is precisely why the idea matters so much, beyond its strangeness alone. If information genuinely exists in two places at once, quietly redundant, connected through the deep language of quantum entanglement, then the entire notion of inside and outside becomes far less like two separate rooms, and far more like two different perspectives, describing, in different ways, the very same underlying quantum reality. It's a profound, careful reshaping of language and geometry both, one that continues to influence how physicists frame nearly every question we've explored so far tonight. Let's shift now, gently, toward a different, more practical branch of this research, one built not from the full complexity of our real universe, but from something delightfully simpler. A separate line of work uses highly simplified two-dimensional gravity models to study black holes, wormholes, and information recovery. Our universe, of course, has three dimensions of space, and one of time. Four dimensions altogether, and the mathematics describing gravity within that full four-dimensional reality is extraordinarily complex, often too complex to solve completely, even with our most powerful mathematical tools. So physicists have developed something wonderfully clever. Simplified models, built in just two dimensions, one dimension of space, and one of time, where the underlying mathematics becomes remarkably more manageable, while still preserving many of the deep, essential features of gravity itself. Those toy models are valuable because they are solvable, so they help physicists test ideas that are otherwise too hard in full 3D or 4D gravity. It's worth appreciating just how important this kind of simplification really is, within careful scientific research. These simplified models are often affectionately called toy models, not because they're unserious, but because, much like a toy version of a much larger machine, they capture the essential moving parts, in miniature, allowing physicists to actually work through the full mathematics, from beginning to end, and arrive at genuine, complete answers. Ideas that remain frustratingly intractable in our full four-dimensional universe can often be explored thoroughly, and rigorously, within these simplified two-dimensional frameworks instead. Researchers have also used simplified gravity models to explore whether information can survive a black hole to white hole transition. And this brings that toy model approach directly back to the very heart of tonight's larger story. Using these simplified, solvable frameworks, physicists have specifically examined whether information, the same information we discussed a little earlier, describing everything that fell into a black hole, can genuinely survive the transition into a white hole geometry. Within these more manageable models, researchers can trace the mathematics carefully, step by careful step, checking directly whether information truly makes it through this proposed transition intact, rather than simply hoping or assuming that it does. Some modern black hole cosmology papers use loop quantum gravity to argue that singularities can be resolved mathematically rather than left infinite. We touched on this idea earlier in our journey tonight, and it resurfaces here for good reason, because it remains one of the most actively developed and mathematically productive threads running throughout this entire field. Loop quantum gravity continues to offer researchers a genuine, careful mathematical pathway for resolving singularities, replacing that troublesome infinite density with something finite, structured, and physically sensible instead. Certain quantum black hole calculations try to keep the Hawking temperature consistent with the classical result for large black holes. This detail speaks to something important about how good scientific theories are built and tested. Whatever new, quantum-corrected model of a black hole physicists propose, it needs to agree with well-established, thoroughly confirmed physics, at least in situations where that established physics has already been carefully verified. Hawking temperature, the very faint thermal radiation black holes are theorized to emit, has a well-known classical prediction for large black holes. And so, these newer quantum models are carefully checked to ensure they reproduce that same, familiar temperature for large black holes, even as they introduce new, quantum-corrected behavior deep within the interior, where classical physics can no longer be trusted. The same framework can constrain model parameters by requiring behavior to remain physically reasonable on observable scales. This is, in many ways, simply good scientific practice, applied carefully to an extremely speculative area of theoretical physics. Any proposed model, however creative or mathematically elegant, still has to behave sensibly in situations we can actually observe, or at least indirectly verify. If a particular set of parameters within these quantum-corrected models led to wildly unreasonable predictions, contradicting what we already know from careful astronomical observation, that would immediately signal a problem, requiring the model to be adjusted or reconsidered altogether. In this way, real-world observation continues to quietly discipline even our most abstract, most speculative mathematical proposals. Some models focus on the Kretschmann scalar, a curvature measure, to check whether the geometry stays finite or develops extreme behavior. Here, we encounter a specific, careful mathematical tool, worth understanding gently, even without delving into its full technical definition. The Kretschmann scalar is essentially a single number, calculated at any given point in spacetime, that captures how strongly, and how extremely, spacetime is curved at that location. Near a classical singularity, this value would rise, without limit, toward infinity, a clear, unambiguous mathematical signal that something has gone catastrophically extreme. By carefully tracking this particular quantity throughout their quantum-corrected models, researchers can check, directly and rigorously, whether their proposed geometry genuinely remains finite, well-behaved, and physically sensible, or whether, despite their best efforts, some hidden, extreme behavior still lingers, quietly, somewhere within the mathematics. Some black hole models are built as effective quantum gravity approximations rather than full theories, because full quantum gravity is still unknown. And this brings us to a quiet, honest, grounding thought, worth carrying gently with us as we approach the end of this particular segment. Despite everything we've explored together tonight, loop quantum gravity, Einstein Cartan torsion, entanglement islands, two-dimensional toy models, quantum boundaries near Planck curvature, we still do not possess a single, complete, universally accepted theory of quantum gravity. What we have instead are effective models. Careful, mathematically consistent approximations, each capturing some genuine piece of the deeper puzzle, each offering real, meaningful insight, yet none of them claiming to be the final, complete word on how gravity and quantum mechanics truly fit together, at the deepest possible level. It's a humbling thought, in its own quiet way, that even our very best theoretical tools, however elegant, however mathematically rigorous, remain approximations. Careful sketches, rather than a finished portrait. And yet, perhaps that's exactly what makes this entire field so remarkable to sit with, this late into the night. Not the promise of final answers, arriving all at once, in some single, triumphant breakthrough, but the slow, patient accumulation of careful insight. Piece by piece. Model by model. Each one bringing us just a little closer to truly understanding what might be happening, quietly, endlessly, behind the event horizons scattered throughout our vast and still deeply mysterious universe. We'll rest here for a moment longer, gently, and continue drifting onward, into the facts that follow. We drift onward now, from the quiet, humbling thought of approximations and careful sketches, into some of the most recent, most active corners of this research, where theory begins, ever so gently, to meet observation. Some 2025 theoretical work continues to extend black hole models in ways that connect singularity resolution with quantum gravity phenomenology. Even now, in this very moment, somewhere in the world, researchers are quietly continuing this work. Refining these models. Testing new mathematical approaches. Connecting the careful singularity resolution ideas we've spent so much of tonight exploring, with something called quantum gravity phenomenology, essentially, the search for observable, measurable consequences that might arise from these deep, theoretical frameworks. It's a reminder that this story we've been following together isn't a finished one. It continues to unfold, quietly, in research papers being written even as we speak. Another modern idea suggests the Higgs field might behave differently under extreme collapse, possibly affecting particle masses inside a black hole. Here, we encounter something wonderfully specific and strange to imagine. The Higgs field is the very same field responsible for giving fundamental particles their mass, throughout the universe we experience in our everyday lives. Some researchers have begun wondering whether, under the truly extreme conditions found deep within a collapsing black hole, this field might behave differently than it does out here, in the calmer regions of spacetime we call home. If so, particle masses themselves, one of the most basic, seemingly fixed properties of matter, might shift, subtly, within that extreme interior, hinting, perhaps, that the very rules governing matter could look different, deep behind the event horizon. Some recent speculative models link black hole universe formation to dark matter and dark energy as side effects of deeper gravitational processes. This connection feels particularly compelling because it reaches toward two of the deepest, most persistent mysteries in modern cosmology. Dark matter, that invisible, unexplained mass shaping the rotation of galaxies. Dark energy, that mysterious force driving the accelerating expansion of our universe. Some researchers now wonder whether these two enigmas might not be entirely separate puzzles at all, but rather, side effects, natural byproducts, perhaps, of the very same deep gravitational processes involved in black hole universe formation. It's a beautifully unifying kind of thought, even in its speculation. That the darkness filling our universe, both figuratively and literally, might trace back to the same quiet, hidden physics happening within black holes themselves. Some papers and reports now connect black hole cosmology not only to universe origins but also to broader questions about dark energy and cosmic evolution. This reflects something important about how this entire field continues to grow and mature. What began as a narrow, highly speculative question, could black holes create new universes, has gradually expanded outward, touching an increasingly wide range of cosmological questions. Not just how our universe may have begun, but how it continues to evolve, how it expands, how its darkest, least understood components might ultimately trace back to the same deep gravitational roots. Some recent black hole research focuses on how dark matter changes black hole shadows and gravitational wave signals, which could indirectly inform cosmological models. Let's slow down here, gently, and take this idea piece by piece. A black hole shadow refers to the dark silhouette a black hole casts, surrounded by the glowing, superheated material swirling just beyond its event horizon, the very image famously captured by the Event Horizon Telescope in recent years. Gravitational waves, meanwhile, are ripples in spacetime itself, created by immense cosmic events, like colliding black holes, and detected here on Earth through extraordinarily sensitive instruments. Researchers have begun studying how the presence of dark matter, surrounding a black hole, might subtly alter both of these observable signatures, its shadow, and its gravitational wave signal. And these subtle alterations, in turn, could offer indirect clues, helping to test some of the broader cosmological models we've explored together tonight. Dark matter effects on black hole shadows can alter the predicted appearance of a black hole, which matters for testing related cosmological ideas. This detail carries real, practical weight within the broader story we've been following. If dark matter genuinely does change how a black hole's shadow appears, even subtly, then careful, precise astronomical observations, comparing predicted shadows against actually measured ones, could begin to reveal whether our theoretical models are correctly capturing the true physics at play, deep around these extraordinary objects. It's a quiet, careful way that pure theory begins, gradually, to meet the discipline of genuine observation. Observational progress in black hole astronomy is making it easier to compare speculative universe formation ideas against measurable black hole behavior. And this marks something genuinely significant, worth appreciating fully as we approach the close of this segment. For much of the history we've explored together tonight, these ideas, universe birth, cosmological natural selection, quantum bounces, entanglement islands, existed almost entirely within the realm of pure mathematics. Elegant, careful, internally consistent, but largely untestable in any direct, observational sense. That's beginning, slowly, carefully, to change. Black hole cosmology has become more connected to observational astronomy, especially through measurements of shadows, jets, and gravitational wave signatures. Modern black hole astronomy has grown remarkably sophisticated in recent years. We can now capture direct images of a black hole's shadow. We can observe the powerful jets of energetic particles, launched from some black holes, streaming outward across vast cosmic distances. We can detect the faint, rippling gravitational waves produced when black holes collide and merge into one another. Each of these observational tools offers physicists new, precious data that can, increasingly, be compared directly against the predictions made by these speculative black hole cosmology models. Researchers are now comparing speculative universe creation ideas against black hole data from telescopes and gravitational wave detectors, rather than treating them only as philosophy. This represents, perhaps, one of the most meaningful shifts in this entire field. For a long time, ideas about black holes creating new universes lived closer to philosophy than physics, fascinating to consider, mathematically elegant in places, but seemingly beyond any hope of genuine scientific testing. Now, with these advancing observational tools, that boundary is beginning to soften. Careful researchers are gradually, patiently, finding ways to hold these speculative ideas up against real, measured data, asking, honestly, whether the universe we actually observe, through our telescopes and detectors, behaves the way these theoretical models predict it should. It's a quiet, meaningful transformation, watching an idea slowly grow, from pure imagination, into something approaching genuine, testable science. Some recent black hole research focuses on how spacetime itself may emerge from more fundamental quantum information. And so, we find ourselves circling back, gently, to one of the deepest threads running through everything we've explored together tonight. That spacetime itself, the very stage upon which stars burn, galaxies drift, and black holes quietly form and evolve, may not be the most fundamental layer of reality at all. It may be something that emerges, the way so many familiar, everyday phenomena emerge from deeper, less visible processes, arising from some hidden, quantum foundation we are still only beginning, patiently, carefully, to understand. We have just one more gathering of facts remaining in our journey together tonight. And in that final stretch, we'll bring everything we've explored, the collapses and the bounces, the daughter universes and the quantum boundaries, the islands of information and the telescopes now quietly listening for answers, gently, softly, toward its close. We arrive now at the final gathering of facts in our journey together tonight, and it feels fitting to begin this closing stretch by looking back, gently, at how far this field has traveled. Some recent reviews of black hole breakthroughs emphasize that black hole physics is advancing fast enough that older assumptions about interiors, horizons, and singularities are being actively rechecked. It's worth pausing on this thought, quietly, before we move further. Science, at its best, never simply settles into comfortable certainty and stays there. Even ideas that once felt firmly established, the nature of the singularity, the precise behavior of the event horizon, the fundamental structure of a black hole's interior, are being revisited, questioned, and refined, as new mathematical tools and new observations continue to emerge. Nothing in this field is treated as beyond question. Everything remains open to careful, patient re-examination. New observations have revealed more complex black hole systems, such as black hole triples, which improve our understanding of how black holes evolve in real astrophysical environments. For a long time, much of our theoretical understanding of black holes came from studying them in relative isolation, or in simple pairs, slowly spiraling toward one another before merging. But the universe, as it so often does, has revealed itself to be considerably more intricate than our simplest models. Astronomers have now identified systems containing 3 black holes, gravitationally bound together, influencing one another in complex, evolving ways. These discoveries help refine our understanding of how black holes actually behave and evolve out in the real, messy, wonderfully complicated universe, beyond the clean, simplified pictures theoretical papers often begin with. Recent work has connected black hole universe ideas to observations of galaxy spin patterns from the James Webb Space Telescope. Here, our story takes a genuinely unexpected turn, reaching far beyond black holes themselves, and out toward the largest structures in our observable universe. The James Webb Space Telescope, with its extraordinary ability to observe extremely distant, extremely early galaxies, has provided researchers with a remarkable new dataset, one that has, quite unexpectedly, found its way into conversations about black hole cosmology. In that report, researchers noted that many galaxies appeared to rotate in the same direction, which is unusual under a perfectly random expectation. If galaxies formed entirely independently of one another, through processes with no larger, overarching structure guiding them, we might reasonably expect their directions of rotation to be essentially random. Roughly half spinning one way, half spinning the other, scattered without any particular pattern. Yet, in this particular set of observations, researchers noticed something curious. A larger proportion of galaxies than expected appeared to share the same rotational direction, a subtle, but genuinely puzzling asymmetry, in a universe we generally assume should look the same, statistically, in every direction we look. That kind of rotation asymmetry has been discussed as possible support for a universe that was born rotating. And this is where the observation quietly reconnects with everything we've explored together tonight. If our universe itself inherited some overall rotation, some large-scale spin, from the very process of its formation, perhaps, some researchers speculate, from precisely the kind of black hole collapse and bounce we've spent so many hours considering, that inherited rotation might subtly influence the large-scale distribution of galactic spin directions, even billions of years later. It remains, we should say gently, a genuinely speculative connection. But it's a beautiful example of how a very abstract, mathematical idea about black holes and universe formation might, just possibly, leave a faint, detectable fingerprint, written across the sky, in the quiet rotation of countless distant galaxies. Some black hole universe models try to explain the Big Bang as a transition rather than an absolute beginning. We return here, gently, to an idea we sat with earlier tonight, and it feels fitting to let it settle once more, this close to our conclusion. Rather than picturing our universe as beginning as a sudden appearance from absolute nothingness, these models offer something quieter, and in some ways, more comforting. A transition. A continuation, of sorts, from whatever came before, even if before is a word that barely makes sense, once we're speaking about something existing prior to time itself. Several recent discussions emphasize that these ideas are still controversial and not settled by direct evidence. And here, as we draw close to the end of our long journey together, it feels important to hold this truth carefully, one final time. Nothing we've explored tonight represents settled, confirmed scientific fact. These are hypotheses. Careful, mathematically rigorous, seriously considered by genuine physicists, but hypotheses nonetheless. The scientific community remains divided, and rightly cautious, about how much weight to place on any single version of these ideas. A key challenge is that the interior of a black hole is not directly observable, so the idea is difficult to test experimentally. We began this entire journey with this very obstacle, and it remains, even now, at the very end, the central challenge shaping everything we've discussed. The event horizon keeps its secrets. Whatever is truly happening deep within a black hole's core, whether it's a crushing singularity, a quantum bounce, a transition into a new universe entirely, remains fundamentally hidden from direct observation, perhaps permanently. Physicists must instead rely on careful mathematics, indirect evidence, and patient theoretical reasoning to explore territory they may never be able to visit or witness directly. The broader scientific interest in these ideas is that solving black hole puzzles may also help explain how the universe itself began. And this, perhaps, is the quiet, unifying thread running through every single fact we've explored together tonight. This entire investigation was never truly just about black holes, in isolation. It reaches towards something far larger. Understanding what truly happens within a black hole may hold the key to understanding our own origins, how spacetime itself came to be, how the delicate laws of physics we depend on came to take their particular, finely tuned form, and how something, rather than nothing, came to exist at all. Whether black holes truly create new universes remains one of the biggest unanswered questions in modern physics, but every new observation brings scientists a little closer to discovering the answer. And so, gently, we arrive at the end of tonight's long, quiet journey through the mathematics, the mysteries, and the vast, patient curiosity surrounding black holes and the universes they might, just possibly, contain. We began at the edge of an event horizon, a boundary from which nothing, not even light, can return. We drifted through singularities, and their possible resolution, through bounces in daughter universes, through Smolin's strange, evolving cosmic family tree, and Poplawski's twisting, torsion-filled spacetime. We considered wormholes, and white holes, and the delicate, careful mathematics required to keep these models internally consistent. We sat quietly with the black hole information paradox, and the elegant, hard-won mathematics of entanglement islands, offering a path toward preserving what might otherwise seem lost forever. And finally, we watched this once purely theoretical field begin, slowly, carefully, to reach toward genuine observation, toward telescopes, and gravitational wave detectors, and the faint, rotating patterns of distant galaxies, each offering their own quiet, indirect testimony. No definitive answer awaits us at the end of this particular night. No single, triumphant conclusion, tying every thread neatly together. What we have instead is something gentler and perhaps, in its own way, more beautiful. An honest, patient portrait of human curiosity itself, reaching, carefully, mathematically, toward one of the deepest mysteries our universe holds. Wondering, quietly, whether every ending we witness in the cosmos, every collapse, every silence, every disappearance beyond an event horizon, might, somewhere, in some way we're only beginning to understand, also be a beginning. Rest now, gently, beneath whatever sky you find yourself under tonight, knowing that somewhere above you, hidden within the quiet darkness scattered across the heavens, some of the universe's deepest secrets may still be patiently unfolding.